So we'll draw the velocity triangle for axial flow compressor. So firstly it enters the stator, correct. So once it has come to the stator, it will act like a guide vane now. So now once from stator to rotor stage, so the actual stage is in the rotor stage. So in rotor stage, let your air enter with a certain angle alpha, okay, and then it has to face the rotor blade of U, correct. And now because of these two, the resultant VR, okay, so we'll just name it. This is your absolute inlet velocity, and this will be your rotor blade velocity, so that is U1, and this will be your reaction VR1, sorry, resultant VR1, okay. Now because of V1, you'll have the tangential and radial component, okay. So now this is your V, what do we specify? VW1 for tangential, and radial VF1. This is your inlet triangle of the rotor. I'll just write this: inlet to rotor, okay. And then the next stage is outlet to rotor, also called as inlet to stator, okay. So once it is coming out, now the water will exit at again a certain angle V2. Just draw it little afar. V2. Sorry, I forgot to mention alpha and beta. This is alpha 1, and this is beta 1, okay. So it will exit with a certain absolute velocity V2, and then it will face the same velocity at the root U1, correct. So because U1 and U2 are same, we'll just take it as U. And now the resultant VR1, VR2, and then the usual tangential and vertical component, VF1 and VW1. VR1, sorry, we'll go in order, that is V2, and it will face U1, which is same, so I'll just write it as U, and the resultant of both of it is VR2, okay. And then the tangential component of V2 is VW2 and VW1, sorry, VF1, radial component. See, like these two are same. Since U is same, you can actually draw on a single velocity triangle. Since these two are common, this will be this side and this will be on the other side. You can draw on a single component, but it will be a little confusing, so you can just draw separately alpha 2 and beta 2. Correct. So now this is inlet to stator. So it's inlet to stator, and after coming to stator, what is the outlet of stator? So therefore you have 3 triangles here. Outlet to stator. So once you have outlet to stator, so since you are not facing any u here, correct, so stator will not have any blade velocity, it is fixed. So therefore your u is completely gone, but what you'll have is your v3, an absolute velocity v3, and to it you'll have a certain tangential and radial components. Okay, so this will be your v3, and this will be your vf3, and this will be your vw3 with a certain alpha. Alpha 3. So these are the main generic triangles. Then what you do, you just consider there is one condition. Since this outlet of stator will again be an inlet to the next stage, so in bracket if I write inlet to next stage, correct, so this is an inlet to another next stage. So in that case we make one assumption. I mean, the compressor is designed in such a way that v1 is almost equal to v3. The absolute velocity of the inlet of the rotor will be the absolute velocity at the exit of the stator, which is entering to the next stage. Okay, so therefore, so to put it picture in perspective, v1 is equal to v3, thus implying v3 will be equal to v4. Okay, v4 is the absolute velocity with which the air enters the rotor. Okay, so we'll just take this condition, just keep this condition in head, and then keeping this triangle we can draw out numerous trigonometric relations. I've tried to explain them in class already. What I'll do, I'll just sort of write them out. Keeping these triangles in mind, you just correlate and then find, okay, this sine. Okay, how do you get, say for example, if I have to say what is cos alpha 1, so cos alpha 1, so if you take this cos alpha 1 is equal to adjacent by hypotenuse. So adjacent here is vf1 by hypotenuse is v1. Okay, so similarly you just correlate all of it, and I'll draw all of it and then explain if anything that is assumed or how we have got it. Okay, so we'll just draw out some conclusions here. So we'll just try to segregate alpha and beta. So we know cos alpha 1 is adjacent by hypotenuse, so adjacent is vf1 by hypotenuse is v1, and so that is vf1 divided by v1 is equal to cos alpha 1, and that is also equal to cos beta 2. So cos beta 2 is adjacent is cos beta, so adjacent is vf1 by hypotenuse is vr1, so vr1 cos beta 2, and vw2 tangential component, so sin alpha is opposite by hypotenuse, so v1 sin alpha 1, and tan alpha 1 is adjacent by opposite by adjacent, so vw1 divided by vf1. Okay, and then we have a factor called x. So that is, this whole thing is u, and only this portion is VW1. But this red portion remaining, what you'll denote it? You can denote it as X. One mistake what I've done is, you can take this as X1 for here, and here it is going to be X2. Okay. So once you have given out those conclusions, we know U1 is equal to VW1 plus the remainder of U, that is X1. Correct? So therefore, we can write VW1 is equal to V1 sine alpha 1 plus X1. We don't know the value for X1, correct? But X1 can be written as sine of, in terms of sine. So beta 1 would be, opposite is X divided by hypotenuse VR1. So therefore, X is equal to VR1 sine beta 1. Okay, now keeping this, we can substitute for V1 sine alpha 1. So V1 sine alpha 1 is equal to VF1 tan alpha 1. So VF1 tan alpha 1, and VR1 sine beta 1 is equal to VF1 tan beta 2. So taking VF1 common, we can write tan alpha 1 plus tan beta 2. So U, the rotor speed, will be equal to the, wait, let us define it. The rotor speed will be equal to the radial component multiplied by tan alpha plus tan beta 1. So with all similar conclusions, if you try to draw out conclusions for the second triangle, you'll also get U2 is equal to X2 plus VW2, and then similarly finally you'll get U is equal to VF2, I've written 1 here, let's correct it, VF2 into tan alpha 2 plus tan beta 2. So that is the important conclusion that you'll draw out from this. So you can see V and VF1 and tan alpha 1 and tan beta 2, and V and VF2 and tan alpha 2 and tan beta 2. So what we'll try to do, we'll take a condition where VF1 and VF2 and VF3 all are equal to, so all the axial velocity, sorry, previously I said radial, it's not radial, it's axial velocity. All of the axial velocity is equal to VF. So for a condition like that, what happens? So your VF1 will become VF is equal to V1 cos alpha 1 is equal to VR cos beta 2, and then for the, similarly on the second triangle, it will become V2 cos alpha 2 is equal to VR2 cos beta 2. Correct. Now what you can do, U divided by VF1, U divided by VF1 will now become VF, which is equal to tan alpha 1 plus tan alpha 2 is equal to tan alpha 2 plus tan beta 2. So this is your final relation, and U by VF has got its significance. We'll try to describe it in while we're discussing performance parameters. Okay. If we talk about work input to the compressor, we know previously from all the compressors, from Euler's formula, we can derive work input to the compressor is equal to differential, that is difference of U2 VW2 minus U1 VW1. So since U is common here, U2 is equal to U1 is equal to U, so you're taking U out, is equal to VW2 minus VW1, that is the tangential component of the absolute velocity. Okay. Now using the trigonometric relations, we can write VW2 as equal to VF2 tan alpha 2 minus VF1 tan alpha 1. So since we assumed VF2 is equal to VF1, again we'll take VF common, and tan alpha 2 minus tan alpha 1. Similarly, for beta 2, we can write U into VF2, sorry, U into VF into tan beta 1 minus tan beta 2. So it is tan alpha 2 minus tan alpha 1 and tan beta 1 minus tan beta 2. Okay. And from Euler's energy equation, work input can be written as half of differential of absolute velocity square plus differential of rotor velocity square plus differential of the resultant velocity square Since u2 minus u1 is 0, because u2 is equal to u1, will eliminate this term. The only remainder is half of absolute velocity at outlet square minus absolute velocity of inlet square, plus the resultant velocity at outlet square minus resultant velocity of inlet square. So these are the terms you can use for work input to the compressor. So next we'll talk about the work done factor. Okay, so work done factor, let us assume this to be the axial compressor, and we'll just divide it in some stages. Okay, so let it be like a 15 stage or a 20 stage compressor. So we'll just collectively call 3 different zones. Okay, so in all of the equations what we have said, we have taken the axial velocity component, that is Vf1, to be constant. Okay, but in reality, so you call this as the annulus. Okay, this is called, so the distance from entry to the exit of the compressor, you call it as annulus. So as and when the annulus of the compressor increases, okay, I'll just write it, axial flow velocity Vf. Okay, the axial flow velocity Vf will not be same throughout the axial compressor. So initially it will be somewhat, so if I take in green boxes, so initially it will be somewhat okay up until here, but as and when you come deeper inside, the axial velocity will gradually reduce. Probably I should write it like this. So we'll reduce somewhat like this. Okay, so therefore this is not a constant, but so far what we derived was that W work done is equal to U into Vf and tan alpha or beta. So alpha, it is alpha 2, beta beta 2. So alpha 2 minus tan alpha 1. Okay, so one thing what all we know, I mean, even if you want to see so how work done is varying. So 1 second, so why this phenomena is occurring? So we've discussed in class 1. So like, because the annulus is increasing, the velocity, because the machine is rotor machine, it is rotating, even though the velocity should be axial throughout. So if we take, if let us say if one air molecule has entered here, by the time it will come out of here, it will go through many places. So initially it will be here, and then in the second stage it will be here and here, here. So because of this variation, okay, the boundary layer will not be uniform. Okay, so with that consideration, the overall work done will not be equal to your theoretical work done. Okay, so to avoid that factor, we'll just look at the equation. We know alpha 1 and alpha 2 is designed and it is fixed. Alpha and beta are fixed terms, and U is rotating with constant U because of the common shaft. So the only variable here is Vf. So to compensate this, what we'll add a work done factor called sigma. So therefore it can be written as U into, I can't use a sigma here, I'll just write it, sigma Vf into tan alpha 2 minus tan alpha 1. Okay, and this is also equal to tan beta 1 minus tan beta 2. So this is like a correction factor sigma. So sigma, how you'll draw here is you'll draw it like this. Okay, and the value of sigma will usually vary somewhere between 0.98 to 0.85. Okay, so what this means, the actual work done will be off by a factor of 0.98 and 0.85. So for 100% work, the actual work done would be 98% work or 85%. So the range is between there. So the sigma will add up to the work done. So that is why you call it as work done factor. So while solving problems, if a problem specifically mentions take work done factor to be so and so, then you make use of this work done factor wherever necessary. So wherever you find your axial velocity Vf, you also take along with it a substitution as sigma and then go about it. Okay, let us talk about degree of reaction. So degree of reaction is nothing but, by definition, it is the ratio of actual change of enthalpy in the rotor divided by actual change of enthalpy in the stage. So meaning, what is the enthalpy change that was achieved in the first stage to the overall enthalpy change from rotor to stator. So both the stages combined. So that is nothing but degree of reaction. So first stage is what? From the rotor is 1 to 2, and the enthalpy, overall enthalpy is 1, 2 and 3. So that is 1 to 3. So 1 to 2 divided by 1 to 3. So therefore H2 minus H1 divided by H3 minus H1. So in terms of temperature, we can just write it as T2 minus T1 divided by T3 minus T1. Correct. But we've assumed the velocity at V1 to be equal to V3. Correct. So absolute velocity that is entering at the rotor will be equal to the absolute velocity that is exiting out of the stator, which will in turn become the inlet to the next rotor. So therefore, with that condition, if we assume the overall change in enthalpy will directly be equal to the change in stagnation enthalpy. So why am I saying change in stagnation enthalpy? Because there is no velocity change. So if you just look at this, there is no velocity change. So if you take the total pressure, the dynamic pressure will equalize once in the first stage and then in the second stage. So therefore, with that assumption, we can directly take the enthalpy change from 3 to 1 is directly equal to the stagnation change from 0 to 1. Okay, because the kinetic value, the V is not changing, therefore it is directly equal to stagnation change. So now if the stagnation change is occurring, that is nothing but directly equal to work done in the given stage. So the work done in the given stage is given by U into V tangential of V tangential component of second minus V tangential component of the first. Okay, so now we've got a substitution for H3 minus H1. So that is C3 minus T1, and then H2 minus H1. So we'll just look at what is happening to H2 minus H1. That can be written in terms of relative velocity. So we'll see how is that. So we know actual energy transformation in rotor and stator blade rods occur with stagnation pressure loss and increase in entropy. However, the relative stagnation enthalpy remains same. So when you talk about the actual enthalpy, so actual enthalpy is connected with the absolute velocity. Okay, so when you take the stagnation enthalpy of H01, that will be in reference to the absolute velocity V1. But if you take the relative velocity H01 to the subscript relative, that will be with respect to the relative velocity VR. Okay, so if you take when you see the relative enthalpy change, it is not changing much, but actual enthalpy is changing, whereas relative enthalpy is not changing. So with that assumption, if we take H1 plus half VR1 square is equal to H2 plus half VR2 square. So now taking this substitution, we can write H2 minus H1 is equal to half VR1 square minus VR2 square. So now we'll substitute that for H2 minus H1, VR1 square minus VR2 square. Now, using the trigonometric relations that we have devised earlier, we can write VR1 as VF2 tan beta 1, and similarly VR2 as VF square tan beta 2. So taking that substitution and then another substitution for VW2, we'll simplify this to Vf tan beta 1 plus tan beta 2 divided by 2u and divided by 2u. So what happens here? Vf and Vf get cancelled and one Vf is left out, and then you have tan square beta 1 by tan square beta 2. So this will become tan beta 1 plus tan beta 2 into tan beta, like a square minus b square is a plus b into a minus b. So a minus b and a minus b will get cancelled and your remainder is so much. So to this, what you'll do, you'll take tan beta 1 minus plus tan beta 2, you'll add and subtract tan alpha 1. So if you add tan alpha 1 minus tan alpha 2, you can segregate both of it. So you can take it as tan alpha 1 plus tan beta 1 and tan alpha 1 minus tan beta 2. Okay. So now from the previous case, what we know that is u by Vf is equal to tan alpha 1 plus tan beta 2, which is also equal to tan alpha 2 plus tan beta 2. So with this substitution, I'll write u by Vf for tan alpha 1 plus tan beta 2, and then you can multiply this uf by v inside. So once you multiply this uf by v inside, uf and uf will cancel out, u and u will cancel out, but half will remain. So this is your remainder half, and then you'll have to multiply it to this term too. So this term half is there, and vf by u will be there, and tan alpha 1 minus tan beta 2. So this is your degree of reaction for per stage. Okay. So next, if we talk about 50% stage reaction. So what is 50% stage reaction? So we know the degree of reaction to be ratio of actual change in the rotor divided by actual change in the stage. Correct. So if you divide this, okay, if you divide the overall stage change to equal parts. So firstly, from 1 to 2, that is the rotor stage, and 2 to 3, that is the stator stage. So if you divide the degree of reaction to exactly half of it, you call it 50% stage reaction. So by doing so, what will happen? The burden on the compressor will be reduced. So large pressure rise. So mostly the pressure rise is taking place in the rotor. Correct. So to avoid that indifference, the designer will try to design the stage the degree of stage reaction 50% in the first stage and another 50% in the first blade set and another 50% in the second blade set. So if you take that condition, what it means, the difference in enthalpy from 1 to 2 will be equal to the difference in enthalpy from 2 to 3. So that is half of 1 to 3. So half of 3 to 1 will be equal to this one as well as this one. Okay. So with that assumption, your degree of reaction will become 2. So 1 by 2 is equal to VR1 square minus VR2 square, that is the relative velocity, divided by 2 into u of tangential velocity. So for any case which is greater than half, you'll have uneven division. So at the rotor stage, the enthalpy changes so much. At the stator stage, the enthalpy changes so much. But when degree of reaction is equal, you can see both the conditions are satisfied. So along with that, you get a number of result. So some of the result, I'll just write it directly here. Using all the trigonometric functions, that is alpha 1 will now be equal to beta 2 and alpha 2 will be equal to beta 1. So for designing 50% stage reaction, the considerations are, not the consideration, the consequence of which are like this. And VR1 will be equal to V2. Okay. And VR2 will be equal to V1. Okay. And then you have another important consequence, that is VW1 will be equal to X2. Okay. And VW2 will be equal to X1. So these are some of the important consequences when you design the blade to be in 50% stage reaction.